So machine learning started quite early in 1950s and 1960s, 1970s. We have, and this period was called AI ventures, where government gave the funds, but nothing really happened. When the emails started getting popular, uh, real use cases of machine learning started to emerge, partially also funded by increase in computation, where you can handle a large amount of data, and you were able to. And by 2010, the real breakthrough of deep learning happened, and we were able to classify images. And then using that deep learning, we are able further move into a deep reinforcement learning and GAN, which is generative adversarial networks, which is a further development based on deep learning. We're able to do amazing things like beating humans in Go game, like Lee Sedol, a Korean player, was defeated in a game which he never thought anyone can defeat him, and especially a machine defeating him by 4-1, and he was really surprised. GAN is generative adversarial networks. We know that a lot of deep fakes have come up using GAN, and we will go into the deep details of GAN, how it works, and how we can. We have gone through that machine learning as an example, what it does. But how does humans basically learn? We go to attending a lecture, maybe virtual or a real lecture, or we go and do a hit and trial, like learning in cycling during a childhood, or we do experimentation, right? So these are two ways where the learning happens. So knowledge transfer means you take a bulk of data and try to understand that data, right? Hit and trials is you have a reward system. If you fall, you'll get injured. If you were able to drive cycle properly, then you can go a longer distance. And that's how we learn, right? And so what is actually happening is we are doing only two things, basically. If you think on a mental perspective, we are categorizing the information which we're getting in a lecture and putting into boxes. And we are predicting like what is going to happen next. It could be prediction on anything we want to do. And humans consume information so much only for these two reasons, basically. Because they want to categorize the information, and they want to use this information, whether it is categorized, to predict what is going to happen next. So we ask the machines to do the same, right? For example, using deep learning, you can see that you can classify objects, right? When this is a person, this is a car, this is a helmet. And we try to predict, ask them to predict something like whether the housing pricing is going to go up. And in current case, it would be whether the coronavirus is going to spread or not, right? So we want to make a predictions, and we have different models for it, right? So how do we do that? So there are three basic approaches which we have in machine learning, which is called supervised machine learning, where you use the existing data. So we want to make a predictions, and we have different models for it, right? So how do we do that? So there are three basic approaches which we have in machine learning, which is called supervised machine learning, where you use the existing data. And then there is a unsupervised learning, where basically you don't have the results, but you just know that there is some data there, and you try to understand, make a sense out of it. Chat. Okay, and then in layman terms is basically it is making computer learns from experience, and it is mostly task driven. Let's take an example here, right? What happens? We have an input which we give in a real world scenario, and we get an output. For example, we know that if the bank rates increases, what happens to the housing prices, or if the bank rate decreases, what happens? And we know the outputs. So we make a model out of it using input and output only, ignoring the real world is a kind of a real world algorithm going in the real world. So we want to replicate the real world as a model here. And in future, any inputs comes, so we should be able to predict the output. So that is what we want to achieve. And the more we have the input and output combinations, the better our model is going to be, because it's able to handle all the scenarios based on supervised learning, right? Example of supervised learning is something like whether you want to classify a tumor. You can see that you can use, okay, this is a benign and this is malignant. How do we know that? Because we already know this tumors have a characteristics of this, and then we can have a regression saying, okay, you know, the one which is separating this line, anything which comes, any tumor comes this side, any new tumor comes on this side will be malignant, and any new tumor which comes this side will be benign. So based on, this is called categorization. This is what we're trying to do. Prediction is something like a housing market price, which say, okay, I have a housing market data like cost and size. What would be the price? Can I predict the price based on the size and square feet? Of course, you can put a time as another feature, and it will be more complex graph. But yes, the idea is you're trying to do a prediction. This is a very basic of examples of supervised learning. Unsupervised learning is something where you don't have labels. Means you know there is data, but you don't know whether it's benign or malignant. Like, you know there is something happening, especially in the medical field. It's important, right? You know these are kinds of proteins, but you don't know their function, what they are right now. You just know that they are different, and you say, okay, these are this kind of proteins and these are another kind of proteins, and you just classify them, right? You can do this by a clustering mechanism. Clustering is nothing but calculation of in a very layman's term, calculation of a bunch of objects which are very close to each other, right? So, and you can do it using various algorithms and various parameters. So that would be unsupervised learning. And the real world examples of is network intrusion detections. So for example, if somebody has created a new kind of virus or new kind of an attack, which was never done before. So you don't have any existing data, but you know this is not a normal behavior. So you can easily identify, okay, this is not a normal, this is an anomaly. And so probably this is something not safe, because I know what is safe. So even I have not labeled it, so I will be able to handle it. Second would be clustering your customer base. Now you don't know your customer what they are going to do, but you at least know that they have similar trends. So probably you will go later on, go and dig what they do, but you can say, okay, they have similar trends, and probably I can create some campaigns on top of this. So unsupervised learning helps you in creating a very initial step. I don't think unsupervised is used in a purest form. Unsupervised comes in the very beginning or in stages where you want to do a real-time analysis, especially in social media prediction or something like it. So you want to see whether this is an anomaly or this is something new coming up. So it is always used in a combination with other techniques. So reinforcement learning is the third approach. And reinforcement learning is saying, I cannot know everything. I cannot know what is going to be in advance. It is the same method we discussed, like hit and trial method during childhood. We learn the same mechanism. And here you see that a robot is trying to learn how to play table tennis. So what is basically happening is this robot has been configured to be rewarded every time it hits a ball. And with a hit and trial, it learns how to keep on playing so that it doesn't lose. So that is called reinforcement learning. And this is what has been explained here. You take an action, you interact with the environment, and then the rewards happens, okay? And this is called reinforcement learning, okay? One of the examples of reinforcement learning is AlphaGo, which defeated Lee Sedol, the 9 player. Now, what really happened in this is, as you say, that if it lose, you can have a reward, or if it is uh, -1 as a reward, and if you win, it has a +1 as a reward. And what it does is you define a policies. This is a policy, you will say, right? This is a policy which you have defined, and the computer will place certain steps in advance, like 40 steps in advance, and see whether it is winning or losing. And based on that, it will decide whether it wants to go ahead and play this current move or not. Every time a move is done, the user will also play, right? Lee Sedol is also playing. And again, it is calculated whether it is moving or winning. And that's how it was able to basically defeat Lee Sedol. Now, there is an ethical question whether we should, if machine gets so intelligent, should be scared about it. But I think you should watch the documentary by AlphaGo and Lee Sedol. It helped Lee Sedol to improve its game. That's something unique. He cannot find a human to improve his player because he's already done 9 player. So he was able to improve his game based on the AlphaGo's performance. So I think in future humans will be improving their skills using AI, and I see a lot of scope in this. So this is what it is being saying, no direct training samples, need for exploration. But AlphaGo was trained, I would say that AlphaGo was trained, again, the reinforcement learning, it started from the scratch, but it was played against many of the players move, and so it already have some information. It is not purely a reinforcement learning as such. So need of exploration of environment, yes, that is what is required. We need to know what is the environment itself, and the environment itself is unknown. I cannot know what is going to happen. If you take the number of combination on a go, it's more than the number of stars in the universe probably. So you cannot have all the combinations, not the stars in the universe, but at least in this galaxy, I would say. So you cannot network. What is a neural network? You always hear about it. A neural network. What is a neural network? So neural network is nothing but is electronic representation of the biological neuron. Think of a neuron as something as a muscle, which it, as you go to the gym, you lift weights, your muscles are trained to handle different kind of weights, right? So something similar happens with the neuron. The amount of information you give them, more and more information. So this is what an example would be. Like, for example, in the current situation, you want to know whether the person will be visiting a hospital or not, based on his age, gender, distance, income, how many he has usually visited in the past. That will give you a prediction whether this person is usually getting sick in the past or not, or so you can visualize whether this person can be going to a hospital for a coronavirus case or not. And I will just try to play a video here which explains you how the neural network is constructed. This is a special kind of neural network called NEAT, but it gives a very good example. So I'll try to play this.
Learned all of these things through a process called neuroevolution. In this video, I want to teach you about how Mario learned to beat this level, Donut Plains 1, what its brain looks like, and how it's all based on actual biological evolution. So let's start out by actually looking at Mario's brain. Let's play it again, but this time we'll look at Mario's brain as it's making the decisions of what buttons to press. It's going to look a bit complicated at first, but don't worry, I'll break it down for you. This structure of colored lines and blinking boxes is called a neural network. It's a simple mathematical model for how a brain works, but it can produce some very complicated behavior. With enough computational power, a neural network could come close to simulating a real human brain, but modern technology isn't there yet. On the left side, you have the inputs. This is what Mario sees. It's a simplified view of the level. The white squares stand for blocks the player can stand on, and the blacks.
So basically, this is the environment which is seeing, and these are the neurons which is controlling, right? And on the top, you have a fitness score, which is saying the reward. So maximum fitness. So every time it iterates, it calculates the fitness score.
Squares stand for moving objects like enemies or mushrooms. On the right side, you have the outputs. These are the 8 buttons that Mario is able to press by using its neural network. In between the inputs and the outputs, all those lines and boxes, those are the neural network. Each free-floating box is called a neuron, and the lines connecting those boxes are like the axons and dendrites in a human brain. At any given time, only some of these neurons and connections are actually being used, and this is what people talk about when they say you only use 10% of your brain. The neural network you're seeing is a pretty complicated one, and it got so complicated as a result of a 24-hour evolutionary learning session. So to explain how neural networks work, let's rewind about 24 hours and look at how the whole process started. This is what Mario looked like at the beginning of his training session, all the way back in generation number 0. The program is probably even dumber than you thought at this point. Often it just stands there and doesn't even press any buttons. If Mario stands still for too long, it'll cut off the simulation and try the next neural network. So it's mostly just jumping from one simulation to the next. But occasionally, the neural network says to press the right button, and the player starts walking right. Behavior isn't complicated, but it's enough to make at least some progress in the level. Let's take a look at a sample neural network to understand just how that works. This is one of the randomly generated neural networks that appeared in the first generation of the simulation. There are some green lines and a red line, and one neuron in the middle. Here's how it works. The green line is a positive connection, and the red line is a negative connection.
So I think you got a gist of it, what it is basically happening, how it is getting generated. So my idea was to just give you a very quick understanding. Okay, so what is deep learning? Deep learning is very basic. It says that if you have more than 3 layers, it is deep. That's the very basic definition of 3. But today we see that the deep learning have more than 3 layers, sometimes 12, and they are pretty complex, right? So let's have a look of a deep learning network. So something it will look like this, right? I'll not go into too much of the details, but what it's trying to do is extract some features, right? And those features are being used to do a facial detection. Now, this have a lot many neurons and lot many weights in between to do a facial recognition, right? But what is actually happening here, I will tell you, is in a simple layman terms, there is so much information on the screen, on a face, that we try to reduce the information into smaller features. And that features is basically used to construct a facial model for you, right? And in different angles, in a different possible ways. And that information is used to, so first the information reduction is happening. And then we are predicting what would be the information, and then we are reconstructing it. This is not a complete diagram of facial recognition, but it is something similar to it, right? Next is, would say, auto coloring. So you can also color some automatically the fires. So you can see that you can take a black and white and fill up the colors. So I think this is not appearing right now, but I think you get the idea about it. And then the segmentation, like you take a road and you can segment whether this is a road or this is a stone on a road or a shadow or something. Because if you want to make a autonomous driving, you should be able to segment where you're driving at the first place, right? So only on the road you can drive. And of course, there are other features important in driving, which we'll see in the next few slides. These are some applications of deep learning. So when it comes to forecasting, We have some models called, again, we have a training and a testing data set, which we take from the real world and try to simulate in what could be the prediction about it. The difference here, it is from a normal machine learning, is it uses data in a different aspect. It considers whether it is seasonal, whether it is a trend, and the models like ARIMA, which is stand for auto-regressive incremental moving average, that's basically tells you whether the price will move up or down. It gives a trend, and also takes some amount of randomness. For example, takes an Amazon stock forecast. It was able to predict a bit of forecasting, say to 2014. It is predicting an upward trend, but as you can see, it has outperformed the prediction. So there's a lot of information missing as such as well, like what is the news coming up, what is the regulatory process, how it affects. Those kind of modeling has not been done. And in future, many of the companies are working to inculcate those kind of apart from technical indicators, they are also trying to inculcate indicators and sentiments of the news, how they impact, and which sources impacted how much. So this is about forecasting. And what next? We have gone through what has happened already, and you know already we have softwares, AI softwares like speech recognition, which is pretty much used in Alexa or Google Assistant. We have GPU accelerators, which enables you to quickly do AI compared to traditional CPUs. We have heard a lot about talk about autonomous vehicles, and it shows in throes of disillusionment. The reason is there has not been a real breakthrough in autonomous vehicles, and there are regulatory hurdles as well. Though there are companies who have successfully able to demonstrate autonomous vehicle. We have a project in AIGeeks where we want to try to solve a part of the problem called collision predictions. We want to solve only that part and not get into our regulatory hurdles. We will discuss in next few minutes. Second is what has been there is a computer vision, which is being effectively used and in solving some of the problems like image annotation. Also, it is computer vision is used extensively in various aspects. It is used in also in manufacturing to detect faulty pieces, and there are various ways to. Many people have heard about robotic process automation. It is nothing but you are trying to develop a workflow where you will be using at certain places certain AI. For example, if you're scanning a document, you will use optical character recognition, which is a kind of an AI, and you can use that to automatically fill some forms. So that is another aspect of RPA. Then comes is natural language processing, which we extensively is in a very advanced stage right now, I would say. Though it is still coming and certain improvements has to be done, but we have sentiment analysis as a part of natural language processing. We are able to summarize data very efficiently. We have a graph analytics, which is another way of doing machine learning rather than using traditional databases. So we have a graph network. Deep learning, we just went through deep dive into some of the applications. Auto ML is something where you don't have to know about the right algorithm. You don't have to train manually. What you do is you make a data pipeline and feed it into an auto ML, and it finds the right algorithm and the right parameters for those algorithms automatically, and their model is trained. So auto ML is moving in that direction. It is not yet perfect because there are so many models keeps on coming, and auto ML has to inculcate all those models, and hence it has not been able to. It is very hype, but I think there will be a certain more improvement need to be done when we achieve the high productivity. Digital ethics, this is one topic we want to talk further. We will talk about it as well. Digital ethics is something how to make sure that AI is getting utilized ethically, and it is not being used for nefarious purposes, or the bias of the societies are not part of this taken into the model itself. And quantum computing is one more interesting if you want to solve the problems of the universe and you want to simulate how the galaxies are formed, bigger computation problems like if you want to predict the global weather or climate change, quantum computing comes to rescue. We are doing, as a part of AIGeeks, a meetup in a collaboration with Microsoft, where you will be introduced to a concept of quantum computing. Next is smart robotics. Smart robotics is something very interesting. The robotics we have, we can be added with AI features like computer vision and natural language processing, and your robots are basically equipped with AI is getting developed. So this is one aspect. Edge AI is another term which is related more to infrastructure. So probably you don't want the AI to be located in some central location. You want to have models locally somewhere in your neighborhood on your edge server, and so that the latency between the AI responding to your request, especially the speech and speech recognition or computer vision, is minimized. And then we have a lot of developer toolkits. These are the terms which are coming up in basically data labeling and annotation services. There are many companies which are trying to do. Scale.ai is one of the companies which provides open data itself, and there are various companies who wants to label the data and want to sell that for various purposes, on which application like autonomous driving can be built. So some of the will be moving faster. AI cloud services. So AI cloud services are already provided by various cloud providers like Google, AWS, and Microsoft. They provide various AI services like speech recognition and natural language processing, sentiment analysis, to name the few. There are others as well. Decision intelligence, where you want to take a decision, is more like a something comes from a reinforcement learning as well. So you have certain key aspects entered, like policies into the, and you want to basically replace the CEO of the company. You have all the policies feed inside into the in the policies of a reinforcement learning framework, and it should be able to take a decision. Neuromorphic hardware, this is quite revolutionary. So all this AI is getting developed on a GPU accelerator, and GPUs are pretty energy intensive. So the idea of neuromorphic hardware is that it is a neural network on a chip. Whatever we have seen as a neural network was a software. We are doing a coding on a software level. But if you can make a neural network on a chip itself, it is much more energy efficient, much more smaller, and as a result, you will be able to compute quickly. Some progress has been done, especially by Spinnaker Technologies, which has been able to demonstrate a supercomputer just in a very small box, efficiency of a supercomputer in a very small box, using neuromorphic architecture. Augmented intelligence is adding augmented reality and AR related features on the like, for example, if you have a dash cam, or if you have so it will be able to predict or tell you what is going to happen. Something like that is already there. So there could be a lot of augmented intelligence application in industrial applications where you can have augmented reality on the devices, and the technicians can interact with those augmented reality. Um, AI governance. Now, this is a very interesting topic where we know about data governance as such, but those data governance and privacy laws are not applicable to AI models. So AI models can be anonymized and basically stripped off all the privacy, but it will have certain attributes of basic clusters of the users, and those AI can be used to classify the citizens of various countries and their behavior and predict their behavior. So this is a very contentional and hotly debated topics. Most of the world leaders don't understand how AI works, and that's the reason we don't have a very strong AI governance policies where the AI can be taken out of the country itself. Reinforcement learning, we know that we have just seen an example of AlphaGo, how it is able to predict 40 or 30 moves ahead of the competitor and make a strategy accordingly. And AI marketplaces, which is coming up, where that I can make a model and put on a platform. This is called AI democratization, where a small group can go ahead, put their AI model on the platform, and you will be quickly able to develop an API on top of it, and you can start selling as a service. So that is an AI marketplace. Artificial general intelligence, which is very hotly and long evolution time. So all this intelligence we have taken is all about specialized intelligence like computer vision, audio intelligence, natural language processing. So these are very specific to purpose. But there are emerging trends where you are combining two or different kind of specific AIs, and you can tend to move towards artificial general intelligence. One is if you can deeply integrate with reinforcement learning, and you can start making tools where computer vision and natural language processing is used in a combination, and then the intelligence can learn from it. An example would be, for example, I want to write a story script. So first it tries to give me, I type a story script itself, and it generates a movie for me, but I don't think it's the right movie. So with an experience, he can come to know what kind of movie I want to frame using natural language processing and computer vision.